Everyone dancing under those walkways has about a minute to live, and the reason is a single change on a single drawing. July 17th, 1981. The Hyatt Regency in Kansas City, barely a year old, is hosting a tea dance in its enormous glass-roofed atrium. Somewhere around 1,600 people are there. Above them hang two suspended walkways, one on the fourth floor, one on the second, with the fourth hanging directly over the second. At 7:05 in the evening, both come down at once. 114 people are killed and more than 200 injured. It stood as the deadliest structural collapse in American history until the World Trade Center, and the cause is simple enough to explain in 90 seconds. Start with what a walkway like this actually is. It's a bridge indoors, a steel and concrete deck spanning the atrium with nothing under it. All of its weight, and the weight of everyone on it, has to travel up through hanger rods into the roof structure. That path is called the load path, and the single most important discipline in structural engineering is being able to trace it, every step from a person's shoes to the ground. Here's the original design. Long threaded steel rods run from the atrium roof all the way down past the fourth floor to the second. The fourth floor walkway hangs off those rods at one point. The second floor walkway hangs off the same continuous rods lower down. Each walkway's weight goes straight into the rod and up to the roof, independent parts. Now look at how each walkway grabs its rod, because this is where the whole disaster lives. The walkway is built from two channel beams welded toe-to-toe into a box shape. The rod passes through a hole in that box beam, and a nut and washer under the beam hold it up. So the entire weight of that walkway is bearing on a washer, pressing up against the underside of a welded box beam. That connection was, even in the original design, already marginal. Later analysis found it fell short of the Kansas City building code before anyone changed anything. Then came the change. The steel fabricator looked at the plan and saw a construction nightmare. To build it as drawn, you'd have to thread a nut up more than 20 feet of rod, over threads that would be damaged and dirtied on the way for every connection. So they proposed a simpler version, use two shorter rods instead of one long one. The upper rod runs from the roof to the fourth floor walkway. The lower rod runs from the fourth floor walkway down to the second floor walkway. That sounds like nothing. It's a fabrication convenience. It is also structurally a completely different building. Trace the load path again. In the original, the fourth floor connection carries the fourth floor walkway, and that's it. The second floor's load goes past it, into the rod, up to the roof. In the revised version, the second floor walkway now hangs from the fourth floor walkway. So the fourth floor box beam connection carries its own walkway, plus the entire walkway below it, plus everyone standing on both. The load on that connection doubled. The investigators used an analogy that has been taught in engineering schools ever since. Imagine two people climbing a rope. In the original design, each person grips the rope independently. Each supports only themselves. In the revised design, the lower person lets go of the rope and grabs the upper person's ankles. Nothing about the rope changed, but the upper person's grip now has to hold two people, and that grip was already barely adequate for one. The change was communicated by phone and shop drawing, marked up and approved. There is no evidence anyone performed a calculation on the revised connection. Everyone in the chain appears to have assumed it was somebody else's job. The fabricator assumed the engineer of record would check it. The engineer of record's office stamped shop drawings as a review of general conformance rather than a full recalculation. The number nobody ran would have taken a first-year engineering student a few minutes. So why did it hold for a year? Because structures usually have reserve. Materials are stronger than their design minimums, and the walkways spent most of their lives nearly empty. A few people crossing at a time is a small fraction of design load. It was already deforming too. During construction, a section of the atrium roof had collapsed which should have prompted deeper scrutiny of the whole structure. And in the months before the failure, hotel staff reported the walkways moving noticeably when people walked on them. The night of the dance was the first time those walkways were heavily, statically loaded. People stood on them to watch the dancing below. Now the mechanics of the actual break. The nut and washer under the fourth floor box beam are pressing up into welded steel. The load is concentrated on a very small area, right at the weld between the two channels. A stress concentration, exactly where you don't want one. As the load increased, the steel around the washer began to deform and the washer started to pull through the beam, tearing it open along the weld line. Once one connection let go, its share of the load slammed onto the neighboring connections. As a shock, they failed almost instantly, and both walkways, 65 tons of steel and concrete, fell into the crowd. Firefighters and rescue crews worked through the night, at one point using jackhammers and hydraulic equipment amid water from broken sprinkler pipes. How did we fix it? The Hyatt is arguably the most influential engineering ethics case in American history, and it changed the profession in 4 concrete ways. First, responsibility for connection design got nailed down explicitly. Contracts and professional standards now make crystal clear who checks a shop drawing change, and that the engineer of record retains responsibility for the structural adequacy of what's actually built. I assumed they checked it, stopped being an available answer. Second, the engineers of record lost their professional licenses in Missouri, and the case is now taught in essentially every engineering ethics curriculum in the country. Licensure exists precisely because that stamp is a personal, legal commitment. And this was the case that demonstrated what the stamp means. Third, it accelerated the profession's focus on structural redundancy and robustness. The Hyatt walkways had no alternate load path. The failure of one connection doomed the entire assembly. Modern design for public structures pushes towards systems where local failure gets contained rather than cascading. Fourth, and most practically, it hardened the change review process itself. The lesson isn't don't change designs. Changes happen constantly on real projects. It's that a change to a connection is a change to the load path. And every load path change gets recalculated from scratch by someone qualified in writing. Tacoma Narrows failed because the physics wasn't understood yet. The Hyatt failed with the physics completely understood, on a calculation any competent engineer could have done in an afternoon. Nobody was assigned to do it. But sometimes engineers do all the math right on solid ground and still lose, because sometimes the ground is the thing that's lying to you. Next, the dam that killed 2,000 people and never broke. Subscribe. Every disaster has a failure point.